Welcome to session 2 of Unit 2 in learning the course Design and Analysis of Algorithms. In our previous session, we discussed about the general method of divide and conquer strategy. In this session, we are going to discuss about the first application of divide and conquer strategy, which is nothing but binary search. The main objectives of this session are to know what is binary search problem, to solve binary search problem by using divide and conquer strategy. The learning outcomes of this session are understand the binary search problem and able to design algorithm for binary search problem and also analyze the algorithm for its time complexity. The contents that we are going to discuss in this session are the problem statement of binary search, algorithm for binary search, and also solving an example and also seeing its time complexity. Coming to the problem statement of binary search, the problem statement is given an array of n elements A of n. Here you have given an array A which contains n elements and an arbitrary value x. Here you also given an arbitrary value x. Binary search problem is defined as searching the index of the element x in the given array. Here the binary search problem is we have to search the index of element x in the given array A. If x is not present in the array, it returns -1. This can be done. The divide and the binary search problem can be solved by using divide and conquer method. So this can be done by dividing the array into two sub-arrays and by following divide and conquer strategy. Here we are going to do this binary search problem by following divide and conquer strategy. That is, here we are dividing the given array into sub-arrays and we are following the divide and conquer strategy. That is, we are solving those sub-problems. Here the constraint that we need to know for binary search problem is the given array must be sorted. The given array must be in sorted. If you have given an unsorted array, first you need to sort the given array, then apply divide and conquer approach to find the index of such element x. Okay, the time complexity of binary search is big O of log n. How the time complexity of binary search becomes big O of log n, I will explain that later in this session. So first let us see how to solve this binary search problem. Now here, let us see the process of binary search. hope you enjoyed the video. That video explained how binary search problem can be carried out using divide and conquer method. If it is not understand, there is no problem. I will explain you how it works. So first, before going to explain about that binary search problem, first I am going to show you the sequential searching. That is linear search process. What is linear search process? Let us see here the linear search process. Here I have given 17 elements whose index values are represented from 0 to 16. Whose index values are represented from 0 to 16. Here the search element is 37. In linear search, first the element is compared with the 0th element. If it is not equal, then it is compared with the next element. Then it is compared with the next element. Then it is compared with the next element. This procedure continues till the search element is equal to any of the element in the given array. Now here you can observe at the 11th place, at the 11th index, the search element 37 is present. So in linear search, it takes totally 11 steps to search the given element or to find the index of the given element. Now let us see the binary search problem. Now how to solve this binary search problem? So for solving this binary search problem, here I have given 10 elements. The index values of those 10 elements are given from 0 to 9. So here the key element is given as 31. Key element is given as 31. Now first what we need to do in case of divide and conquer method, we need to divide the problem into subproblems. Here what is the size of n? Here n is equal to 10. That is totally 10 elements are given. Since n is equal to 10, this is a complex problem. If n is equal to 1, then it is a small problem. But here n value is 10. So it is a complex problem. So we need to divide the given array. Where we have to divide the given array? We need to find the mid value. At mid we are going to divide the given array. What is mid value? Mid is low index plus high index by 2. What is mid value? Low index plus high index by 2. What is low index? 0 plus what is high index? 9 by 2. So which gives 4.5. Here we can take either 4 or 5. We can take either 4 or 5. Here I am considering 4. Here that is at 4 we are dividing the given array. So by dividing the given array at 4, we will get two sub arrays. First we are comparing the key element with the mid element. What is the mid element? 27 is the mid element. First I am comparing that key element with the 27. Since both are not equal, I am going to find whether the given key element is greater than the mid element or less than the mid element. Let us see. Here the mid element is 27 and our key element is 31. That 31 is greater than 27. 31 is greater than 27. So where that 31 may present in the given array? After 27. How we are saying that 31 is present after 27 only? We already said that the constraint for binary search is the array should be in sorted. The array should be in sorted. Since it is the sorted array, the lowest values are present in this side and the highest values are present in that side. If you find the mid value, all the values which are present after mid are greater than it. All the values which are present before mid are less than it. Since our key element is greater than mid element, so the possibility of presence of our search element is second subarray. So we need to continue the process to search this subarray. No need of considering this subarray. The search element is not present in the left subarray. It may be present in the right subarray. So we need to continue the searching process to the right subarray. Now in this case, what becomes low? What becomes low? 5. Low becomes 5. That is mid plus 1. Low is mid plus 1. So low is 5. What becomes high? High cannot be changed. So high is 9 itself. So what is mid value? Mid is equal to low plus high by 2. That is 5 plus 9 by 2, which returns 7. Which returns 7. Now I am going to compare the search element with the mid element. Here the mid element is 35. The search element is 31. 31 is not equal to 35. So since it is not equal, I am going to find whether it is less or greater. 31 is obviously less than 35. So it may be present in this subarray. Here we get two subarrays. This is one subarray and this is another subarray. But the search is not proceeded to this subarray. We are going to search this subarray only. That is only left subarray we are searching. In this case, low value is not changed, which is 5, but high value is changed to mid minus 1, which is nothing but 6. Here we get mid value as 7. It becomes 6. Now again I am going to find mid value. Mid is equal to 5 plus 6 by 2, which gives 5 with mid value. Both are equal. Now we need to return the index 5. We need to return the index 5. So here the search element is found at 5th index. Now let us see the binary search process. The same example what I seen for linear search. Here also I given the same example which contains 17 elements. Here you can observe low value, mid value, high value, how they are changing. Let us observe this video. Yes, see this video. Now here the process for this binary search is completed within 3 steps. The same example we did in linear searching, which taken 11 steps. Let us see the comparison between those two, binary search and linear searching. Here I given the comparison between those two. Here you can observe the same search element within the same array. The linear search taken 11 steps and binary search taken 3 steps. Within 3 steps the process is completed. So we can say that the binary search is efficient process when compared to that of the linear searching. That is, it is having less time complexity when compared to that of the linear searching. So here let us see the algorithm for binary searching. Here we have 2 algorithms. One is iterative binary search and other is recursive binary search. Let us see the iterative binary search. See the algorithm first. Low is equal to 0, high is equal to n minus 1. Here low is low index of the array, high is high index of the array, which are indicated with 0 and n minus 1. Since we have taken an array A which contains n elements, since there are n elements in the array, the index values are represented from 0 to n minus 1. While low less than or equal to high, what we are doing? Mid is equal to low plus high by 2. There we are finding the mid value to divide the given array. First I am comparing the search element with the mid element. If search element is equal to mid element, we are going to return mid value. Else if this condition is false, we are going for this. Else if x less than a of mid, in that case high becomes mid minus 1. Why high becomes mid minus 1? Since the search element is less value, the element may be present in the left subarray. So since we are searching the left subarray, the high value becomes mid minus 1. Else, if this condition is also false, we are going for else. In this case, low becomes mid plus 1. Why low becomes mid plus 1? Here x not equal to a of mid, x not less than a of mid means x greater than a of mid. In that case, the possibility of presence of search element is right subarray. So in case of right subarray, low value becomes mid plus 1. So here the low value becomes mid plus 1. Now I am going to explain the iterative binary search by taking an example. Let us see the example. Here I have given some elements in the array. Let us consider here I have given 6 elements in the array. The 6 element indices are represented from 0 to 5. Here low value is 0 and high value is 5. Now what we have to do in iterative binary search, while low less than or equal to high, we need to repeat the process. Now what is low? 0, less than or equal to 5. Since the condition is true, we are going to find mid value. What is mid value? 0 plus 5 by 2, which gives 2. That is, we are dividing the array at 2. So here we will get 5, 10, 15 as one subarray and 2, 25, 30 as another subarray. Here my key element is 25. I am going to compare mid value with key element. Here key element is 25 and A of mid, that is A of 2. What is A of 2? 15. Here mid element is not equal to key element. Now I am going to see whether it is less than, else if 25 is less than mid value or not. It is not less than mid value. Else what we are taking, since it is greater than mid value, we are going to search the right subarray. In this case, low becomes mid plus 1. That is 2 plus 1, which is 3. Here low becomes 3. Again we need to check the condition. 3 less than or equal to 5. Again condition is true. Now I am going to find mid value. Again 3 plus 5 by 2, which is 4. Now I am going to compare with mid element. 25 is equal to A of 4. What is A of 4? Here this is 0, 1, 2, 3, 4, 5. Here A of 4 is 25. So since 25 equal to 25, we return the index, which is nothing but 4. We find the element at 4 index. This is the iterative binary search. Let us see the next one, which gives recursive binary search. See the algorithm for recursive binary search. Algorithm recursive binary search of A of n low high x. A of n low high x. Now let us see. If low greater than high, return minus 1. So if in processing of your algorithm at anywhere, if low greater than I, you need to return minus 1. That indicates the element is not found. That indicates the element is not found in the array. Now first we are going to find mid value. If x is equal to A of mid, then we are going to return mid value. Else, if x less than A of mid, we are calling the binary search for A low mid minus 1 x. That is, we are calling the binary search for left subarray. That is, the high value becomes mid minus 1. That is, we are calling the binary search for A low mid minus 1 x. Initially we called the binary search for low high, A low high x. Total array we call the binary search initially. But here, since the x value is less than A of mid, the possibility of presence of x is left subarray, we are calling low mid minus 1 x. Else, we are calling the binary search for mid plus 1 high. In this case, if this condition is not true, this condition is not true, in that case, x is greater than A of mid. That is, the possibility of presence of x is right subarray. So, we are calling the binary search for mid plus 1 high. That is, in this case, low becomes mid plus 1 and high. Mid plus 1 to high, we are calling binary search. Now, let us see the example for this recursive binary search. Now, for solving this recursive binary search also, I have taken an example which is nothing but, which contains 6 elements, and here my search element is 25. the 6 elements index values are represented from 0 to 5. Here low value is 0 and high value is 5. What we need to do first? We need to find mid value. Mid is equal to low plus high by 2, which gives 2. Here we are dividing the array at mid, that is at 2. Here we called binary search for 0, 5, that is low to high. Low to high we called. Now here I am going to compare the search element with mid element. Here mid element is 15, that is A of 2. So it is not equal. Else I am going to compare whether it is less or greater than A of mid. Here it is not less. In that case, what we are doing? We are calling binary search of. So the presence may be right subarray. So in this case, low becomes mid plus 1. So we are calling the binary search for 3 to 5. Binary search for 3 to 5. That is, here low is 3 and high is 5. In the earlier case, low is 0, high is 5. So we called 0 to 5 binary search. But here we call low is 3 and high is 5. Again in this case, I am going to find mid value, which is nothing but 3 plus 5 by 2, which is 4. Now I am going to compare the search element with mid element, which is nothing but A of 4. Here A of 4 is 25. Since it is equal, we return the index 4. That is, the element is found at 4. Now here return 4, the index of the element where the search element is found. Now let us see the time complexity of binary search. The time complexity recurrence relation for binary search can be represented as T of n is equal to C when n is equal to 1, T of n by 2 plus C when n is greater than 1. So here, if n is equal to 1, that is, if the given array contains only one element, in that case, the time complexity can be represented with C, a constant. If n is greater than 1, then its time complexity can be represented as T of n by 2 plus C. Now let us see how we are representing the values of A as 1, B as 2 and f of n as C. Let us see here. In case of binary search, where we are dividing the given problem? At mid place we are dividing the given problem. Mid means at half position. So the B becomes 2. I already said you that what is B? B always indicates where we are dividing the given problem, at half place or at 1/3 place or at 1/4 place or at 1/5 place, where we are dividing the problem, that is indicated by B. Since in binary search we are dividing the problem at half place, B becomes 2. And A indicates how many subproblems that we are considering in the process. In case of binary search, every time we are considering only one subarray. If the search element is less than the mid element, we are considering the left subarray. If the search element is greater than mid element, we are considering right subarray. Every time we are considering one subarray only. That's why A is taken as 1. And f of n is the function which is nothing but the time required for dividing the solution, dividing the problem and conquering the solution. Here there is no need of conquering the solutions. In case of binary search, no need of conquering the solutions. Just dividing the problem only we are doing. So that's why the function f of n can also be represented with a constant time, which is nothing but C. Now, by solving this recurrence relation, either by the substitution method or by the Master's theorem, you can get the time complexity of binary search as big O of log n. Now I am going to explain how it becomes big O of log n. Let us see. Here we have given the time complexity recurrence relation as when n is equal to 1, it is C, and this value is T of n by 2 plus C when n is greater than 1. If you compare this recurrence relation with general recurrence relation, you will get T of 1 is equal to C, A is equal to 1, B is equal to 2, f of n is equal to C. Now the time complexity becomes T of n is equal to, now here I am calculating the time complexity by following substitution method. Let us see here what is substitution method. N power log a base b T of 1 plus U of n. That is, here first we need to find U of n. For finding U of n, you need to find H of n. H of n is equal to f of n by n power log a base b. This is equal to, what is f of n? F of n is c by n power log, what is a? 1, base b is 2, n power log 1 base 2. That is n power c by n power 0. Here log 1 is 0. So c by n power 0. N power 0 means 1. That is, we will get c. We will get c. H of n value is c. Now I am going to represent this as c into 1. It cannot changes the value of h of n. If I multiply c with 1, it cannot changes the h of n value. So I am representing that. Now I am writing this one as log n power 0. I am writing this one as log n power 0. Why I am writing like that? H of n should be in the form either n power r or log n power I. It should be present in those two forms only. Then only we will get U of n value. That's why I am writing this as like this. C into log n power 0, which can be written as C into log n power I. Here I is equal to 0. C into log n power I is equal to 0. Now what is corresponding U of n? What is corresponding U of n? If you observe the table what you learned earlier, U of n becomes big O of log n power I plus 1 by I plus 1. So here it becomes big O of log n power I is 0. So 0 plus 1 by 1. So it becomes big O of log n. Now I am going to substitute this U of n in time equation, time complexity equation. So here T of n is identically equal to, what becomes here? N power log 1 base 2 into, here T of 1 is c and U of n is big O of log n. Now here this is equal to again n power 0 c plus big O of log n. So here c is constant. I am omitting the constant and n power 0 is 1. So the time complexity becomes big O of log n. The time complexity of binary search is big O of log n. I hope you all understood the application binary search, which is solved using divide and conquer strategy. Now I am going to summarize the concepts what we learned in this session. In this session, we discussed about the problem statement of binary search, how to solve binary search using divide and conquer strategy, and we seen the comparison of linear search and binary search, and also we see the two algorithms which are nothing but iterative binary search and recursive binary search, which are used to solve this binary search problem, and also we see the time complexity of binary search. To assess yourself, I given some questions here. Answer these questions. The first question is, binary search application follows dash algorithm design technique. Option A, greedy method. Option B, divide and conquer. Option C, dynamic programming. Option D, backtracking. The next question is, in binary search application, the array divides at option A after first element, option B before last element, option C midpoint, option D array not divided. The next question is, implement both recursive and non-recursive algorithms for searching the element x is equal to 42 in the given list of elements. Here I given a list of elements. In this list of elements, find or return the index of the element 42 using both recursive and non-recursive algorithms. For preparing this presentation, I used the digital content from various public sources. This is only used for educational purpose, not for commercial purpose. Thank you for listening the session.